large amount. Now, the thing is that I can get a pure substance by supplying some work into this. So, it's like thinking of these two masses, and if I put one mass on the other side of this wall, which is heavier, and a lighter mass over here, that lighter mass will start to go up. You'll not be able to see the other mass. Right? So the work is being done over there, which is pulling this thing out. So it's not happening spontaneously. Automatically this mass is not getting pulled up, but because of the heavier one it is. So I could use another reaction which gives out more additional work, which is more, so as to say, exergonic. Yeah, there is very interesting terms here. Exergonic. That is delta G is negative. Gives out work. So if it's more exergonic, then I could use that additional work to drive this and get a pure substance. But that is not spontaneous. Okay, so if I have to actually calculate what is the change in the Gibbs free energy for this reaction, then all I have to do it is to sum up the Gibbs free energy of the products minus the Gibbs free energy of the reactant. So let's do it for a more general case than A going to B. Let me write this reaction for mu A, which is the stoichiometric constant of A, and all these are gases for the moment. The temperature is T and the pressure is P. Let's write that. So, more general form of A going to B is A plus B going to C plus D along with the stoichiometries. Now, the Gibbs free energy. Okay, another thing would be that these are ideal gases. So, all A, B, C, D. So, which means I can use the Dalton's law very easily. Partial pressure of any component I would be equal to the mole fraction of I times the total pressure. Right? Now I have to sum up for the Gibbs free energies. So let's say there's the curve that I had drawn. There's a very small change in the reaction coordinate. So the extent of reaction is that small value epsilon. So the delta G for a small change epsilon would be equal to, see, epsilon times nu I, nu C, nu A, nu B, whatever. Epsilon times that nu means that small portion of C has been formed. Epsilon times nu A means a small amount of A has been consumed. So what I'll do is then just write very simply that it's nu C mu C plus nu D minus nu A mu A plus nu B. Just close that bracket. Right. And from some time back, we already know one thing, and that is, let me write that in a different color then mu at a given temperature and pressure is equal to mu naught at that temperature plus RT log P. So mu of component I, P of component I by P naught, which we had already said was 1 bar. Remember this equation?
Yes, sir.
Okay, great. Then using this equation in the above, so substituting this one in the above equation, what I would get is that, sorry, delta G of epsilon would be, so whatever the extent of reaction has been, would be mu C stays there, mu C naught plus mu D naught minus mu A naught plus mu B naught plus I'll collect all these RT log terms, which is R times temperature log of, now Pc to the power mu C, yes, Pd to the power mu D, and since for A and B it's a negative term, I'll just put it down, Pa to the power mu A, Pb to the power mu B. Right? Let me say that my extent of reaction is 1. Say epsilon is 1. So then what I get is delta G is equal to delta G naught, which is the first two terms in the bracket, plus R T log Q. Succinctly, I just write it like this. Okay. So delta G naught is this particular term, where delta G naught is nothing but, okay, is nothing but at the standard pressure, the Gibbs free energy of the products minus Gibbs free energy of the reactants. If that's negative, it's a spontaneous reaction at that standard pressure.
Sir,
Yes?
what is the meaning of epsilon equals to 1?
So I say that my reaction just goes to some completion. So, or whatever, right? Or you could say that this is the change for that small epsilon.
So if it goes to completion, then PA would approximate.
So completion is something. So this is for a small unit of epsilon. Okay, I take that small unit to be 1. Okay, one way. Or this is for that small unit, and I divide it by that small unit. So that's the delta G. Okay. Well, actually, for this treatment, I could have done without the epsilon because I'm not going to do anything further with that, but it's okay. Now, that's called the reaction quotient. Huh? Very nice. So that's the, what happens at equilibrium? At equilibrium, delta G goes to 0, right? So my delta G naught of this particular reaction